You know, electricity, it kind of feels like magic, doesn't it? You flick a switch and bam, there's light. But here's the thing, it's not magic at all. Today, we're going to pull back the curtain and uncover the 3 simple secrets that make the whole thing work. So let's get into it. Okay, so let's start right at that moment. You flip the switch. What is actually happening inside that wall, inside that tiny copper wire, to make a light bulb turn on? It's this beautifully organized chain of events that all starts with one very simple idea. And that first big idea is all about flow. See, to really get electricity, we have to understand what's actually moving in there. And that something that's moving is what we call electric current. Now, the absolute best way to picture this is to just think of a river. The flow of water is, well, a water current. It's the exact same idea in a wire. The flow of these tiny little things called electric charges, well, that's the electric current. It's really just a way of measuring how many of those charges are flowing past a single point. But here's the catch. Just like a river needs a riverbed to flow in, these electric charges need a path too. They can't just go wherever they want. They need a complete, unbroken loop, and we call that an electric circuit. And if you create a gap in that path anywhere, which is exactly what happens when you flip a switch off, the flow just stops, instantly. So if it's flowing, the next question is, how do we measure it? We use a unit called the amp, or you've probably heard it called an amp. Think of it like liters per second for our river. An amp is just a standard way of counting how much electrical charge is zipping past a point every single second. It's just a number for how much stuff is moving. All right, here's a fun little historical oddity for you. Way back when, scientists took a guess and said that it was positive charges that were moving. So by convention, we still draw our diagrams with the current flowing from the positive side to the negative side. Turns out they guessed wrong. We now know it's actually the negative electrons flowing the other way. But, old habits die hard, so the old convention stuck. So we have these charges, and they're flowing. Great. But that brings up the next really big question. What makes them flow in the first place? They don't just decide to get up and go for a jog, right? Something has to be pushing them. Let's go back to our water analogy. If you have water sitting in a perfectly flat pipe, it's just going to sit there. Nothing happens. But what if you hook up a pump? Well, now you've got a pressure difference, and that water is forced to flow. Electricity needs that exact same kind of push. And this electric pressure has a fancy name, potential difference. But you and I know it by its much more common name, voltage. That's it. That's the push. It's the oomph that a battery or your wall outlet provides to get those charges moving around the circuit. And yep, you guessed it. We measure this push in volts. You don't need to get bogged down in the textbook definition. Just know this. A volt is basically a measure of how much energy is behind that push. Higher voltage simply means a stronger push. It's as simple as that. All right, let's do a quick check-in. We have our flow, that's the current, and we have our push, that's the voltage. But there is one more critical piece to this puzzle. Because the path that these charges travel on, well, it's not a perfectly smooth highway. There's almost always some kind of electrical friction fighting against that flow. And we call this friction resistance. Makes sense, right? As these electrons are trying to move through a wire, they're constantly bumping into and navigating around the atoms of the wire itself. It's not a clear path. And that opposition, that property of resisting the flow, is what resistance is all about. And a few key things decide how much resistance you're going to get. Think about drinking through a straw. It's a lot harder to drink through a really long, skinny straw than a short, wide one, right? Same idea here. A longer, thinner wire has more resistance. And of course, the material itself is a huge factor. Trying to push current through glass is like trying to push water through a block of wood. It's just not going to happen. So there we have them, the 3 big players. The flow, which is current, the push, which is voltage, and the friction, which is resistance. And now for the really cool part. There's a simple, beautiful rule that connects all 3 of them together. Now, before I even show you the formula, just think about it logically. If you push harder on something, it's going to move more, right? It's the same thing here. The more push, or voltage, you apply, the more flow, or current you're going to get. It's a direct relationship. It just makes intuitive sense. And here it is, that beautiful rule. Ohm's law. V equals I times R. Voltage equals current times resistance. This simple little formula is the key to pretty much everything in electronics. It means if you know any 2 of those values, you can always figure out the third. This is the tool we use to design everything. And the unit we use for resistance is, fittingly, the ohm. named after the guy who figured all this out. And you can see how it all fits together so perfectly. A thing has a resistance of 1 ohm if it takes 1 volt of push to get 1 amp of current to flow through it. See? It all just clicks.
Okay, enough with the theory. We've got the rules down. But this isn't just about formulas on a page. Resistance is a real, physical thing that gets used in clever ways every single day. So let's see how this actually plays out in the real world.
Now this is fascinating. This chart shows the built-in resistance of different materials. Take a look at silver, a great conductor. Its resistance number is teeny tiny, almost nothing. Then look at glass, an insulator. That number is astronomically huge. And right in the middle, you have things like nichrome, which is an alloy that has a decent amount of resistance. So you might be wondering, why would you ever want something with high resistance? Well, remember that electrical friction we were talking about? What does friction create? Heat. Materials like nichrome are used in toasters and electric heaters on purpose because they fight the current so much that they get glowing hot, but they do it without just burning up. Resistance isn't always the enemy. Sometimes it's the whole point.
And this right here is Ohm's law in action. Plain and simple. You plug a light bulb and an electric heater into the same wall outlet. They're getting the same push, the same 220 volts. But because the bulb has a very high resistance, it only allows a tiny trickle of current to get through. The heater, with its much lower resistance, lets a whole flood of current rush in, and that's what generates all that heat. Same push, different friction, completely different flow.
And this is so important, the source material actually calls it out directly. The big takeaway here is this. The device itself, because of its own built-in resistance, is what dictates how much current it's going to pull from the wall. It's a perfect real-world demonstration of V equals I times R. So we've unpacked the 3 big secrets, the flow, the push, and the friction. And we have Ohm's law, the rule that connects them all for a single component. But let's be honest, real electronics are way more complicated than that. They have lots of different components, tons of resistors. So what happens then? How do you figure it all out when you combine them? Well, that's the next level, and it's a great question to think about for next time.